Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here you have information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. I direct the Actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help ISU actuary. Here is a problem for today for exam LTAM, long-term actuarial models, from the last exam LTAM from fall 2019, problem number 5 in the written answers section. For the single factor longevity model expressed as Q of xt equal to Q of x0 times 1 minus phi sub x to the power t, you are given that base mortality rates are taken from the standard ultimate life table. The following selected improvement factors for ages x equal to 65, 66, 67, and greater than or equal to 68. And the improvement factor phi sub x 0.034, 0.033, 0.031, and then 0.03. Interest rate is 5%, which is the same interest rate that is assumed in the standard ultimate life table. Of course, please remember that you can find the standard ultimate life table at smarturl.it/SULT. K65 denotes the curtailed future lifetime of a life who is age 65 at time 0. Question A. Calculate the probability that K65 is K for K equal to 0, 1, and 2. Part B. Question B. That Y denote the present value of a 3-year temporary life annuity due of 1 per year issued to a life who is age 65 at time 0. Part 1. Calculate the expected value of Y. Part 2. Calculate the standard deviation of Y. Question C. Part 1. Show that this longevity model can be equivalently expressed as P of xt, that's probability of survival, instead of probability of death, which is Q, equal to P of x0 times, is equal to P of x0 times 1 plus psi xt, where psi xt is Q of x0 divided by P of x0 times 1 minus the quantity 1 minus phi x to the power t, for t equal to 1, 2, and so on. Then calculate psi 7010, and then calculate the number of years from time 0 before a life age 70 will have a 1-year survival probability of at least 0.995. Finally, part D. The single factor longevity model has been considered to be too simplistic. Suggest one way to improve the model. And here's the solution. So recall that the model that we're working with is Q of xt is Q of x0, so it's mortality at the same age x, but without moving into the future in terms of the point that we started. So the improvement comes from the fact that the person of the same age but subject to improvement every year by the factor phi sub x has lower mortality as represented by this model. So it's Q of x0 times 1 minus phi of x to the power t. And that base mortality refers to mortality with the 0 after the x, and that's taken from the standard ultimate life table. So we need to calculate the probability that K65 is K for K equal to 0, 1, and 2. And here's the calculation. For K equal to 0, and by the way, just a reminder, Q of 65 plus K, K is Q of 65 plus K 0 times 1 minus phi of 65 plus k to the power k. That's just a different statement of the basic model. So Q of 65, 0 is the Q of 65 from the standard ultimate life table. We look it up. It's 0.005915, so that's what we have for the probability that K65 is 0. Q of 66, 1 is Q of 66, 0. So this is a person who's had a year of mortality improvement. That 1 stands for it. And the person is 66 now, was 65 when mortality improvement or longevity improvement really started. So Q66.1 is Q66.0 times 1 minus phi 66 to the power 1. And then Q66.0 is Q66 from the standard ultimate life table. So now we just plug in all the numbers. So it's 0.006619 times 1 minus 0.033 to the power 1, and that's 0.006400573. And the probability that K65 is 1 is the probability of surviving the first year, so 1 minus the probability we established just above it, times the probability of dying that we just calculated, and it comes out to be about 0.006362714. I'm sorry, for k equal to 2, Q of 67.2 is Q of 67.0 from the standard ultimate life table, times 1 minus phi 67 squared, and that's 0.007409 times 1 minus 0.031 squared, and that's approximately 0.006956762. And the probability that K65 is 2 is the probability of surviving the first 2 years based on the probabilities calculated above, times this mortality probability that we just calculated. And that comes out to be about 0.006871349. For part B, Y denotes the present value of a 3-year temporary life annuity due of 1 per year issued to a life with age 65 at time 0, and we will calculate the expected value of Y and the standard deviation of Y. We note that Y has the following values. Y is 1 if K is 0. Y is equal to A double dot 2 at 5% if K is 1, and Y is equal to A double dot 3, angle 3, angle 2 before, at 5% if K is greater than or equal to 2. So the expected value of Y is just the sum of its values times their probabilities that we just calculated in the table in part A. And I have a typo here, my apologies. That's E of Y squared that we calculated, not the mean of it squared. So this calculation is E of Y squared, the second moment. And it's just the squares of the values times their probabilities, and we get this. And then the variance is E of Y squared minus the mean of Y squared. We just plug in the values we just calculated. And so we calculate that second moment the same way as the first moment, but with squares of values of Y. And then we calculate the variance as the second moment minus the square of the first moment. And I'm very sorry, I had a typo here for a moment. I had 1.84264.085, but of course the second moment is, you can see rather clearly it's got to be more than 2, because this number is more than 2. These are low probabilities, that's true. If the person dies early, that's relatively low probability in this case. So, corrected 2.84264085 for the mean as it should be, because it was there. And then we get the variance to be approximately 0.02540396, and the standard deviation is the square root of that, which is approximately 0.1593861. For part C, or question C, part 1, we have P of xt, the probability of survival. That's 1 minus Q of xt, which is 1 minus Q of x0 times 1 minus phi sub x to the power t. And we write this in a strange way by writing it as p of x0 divided by p of x0. Of course, that's 1. And then we write 1 as p of x0 plus q of x0, and then minus q of x0 times 1 minus phi sub x to the power t. And then we take that p of x0 in the denominator and put it inside, and so the whole thing becomes p of x0 times p of x0 over p of x0 plus q of x0 over p of x0 minus q of x0 over p of x0 times 1 minus phi sub x to the power t. Okay, then you notice that q of x0 over p of x0 is a common factor of the last two terms, so we factor it out, and p of x0 over p of x0 is just 1, so this becomes p of x0 times 1 plus q of x0 over p of x0 times 1 minus, in quantity 1 minus phi x to the power t, and that's p of x0 times 1 plus capital psi xt. So psi of xt is q of x0 over p of x0 times 1 minus a quantity 1 minus phi sub x to the power t. For the second part, we're calculating psi of 7010. That's q of 7010 over p of 7010 times 1 minus phi of 70, phi sub 70 to the 10th power. Now remember that the base mortality comes from the standard ultimate life table, and remember that the improvement factors for ages over 68 are all the same, and they are the phi greater than or equal to 68 factors. So phi 70 is the phi for greater than or equal to 68h. Okay, we look up Q70 in the standard ultimate life table. That's 0.010413, and the bottom is 1 minus that, because it's a probability of survival, times 1 minus 0.03, that's the phi 70, which is really phi greater than or equal to 68, to the 10th power. Of course, 1 minus 0.03 is 0.97, and this fraction in front is 0.010413 over 0.989587, and we calculate on that. That's approximately 0.00276297. For part 3 of that question C, P of 70t is P of 70, which we can look up from standard ultimate life table as 1 minus Q70 from the table, times 1 plus 0.010413 over 0.989587 from the table, of course, times 1 minus 0.97 to the power t, and we want this to be greater than or equal to 0.995. Okay, that is equivalent to saying that 1 minus 0.97 to the t is greater than or equal to 0.995 minus 0.989587 over 0.010413, and that quantity is approximately equal to 0.5198398. So that 1 minus 5198398, which is 0.48016902, is greater than or equal to 0.97. So that natural logarithm of left-hand side is greater than or equal to natural logarithm of right-hand side, which is t times natural logarithm of 0.97. And then we divide both sides by natural logarithm of 0.97, which is negative, so we need to change the direction of inequality, and this becomes t is greater than or equal to natural logarithm of 0.48016902 divided by natural logarithm of 0.97. That's approximately 24,085,2331. So t has to be greater than or equal to that. But t must be an integer, and therefore it has to be 25. So the single factor longevity model has been considered to be too simplistic, primarily because it does not account at all for the so-called cohort effect, which is how the year of birth may affect mortality. And possible ways to improve the model are Use improvement factors that are a function of both age and calendar year to account for the cohort effect. Or the alternative is use a stochastic model, such as Lee-Carter model or a Cairns-Blake-Dowd model, which is also called CBD model. Please remember this is copyrighted material. The problem itself comes from the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.